I cannot see now. I cannot see anything because I am full screen with the slides. So
yeah, that's a problem. You can if you, instead of going full screen,
okay.
you could just select that one window for sharing.
Okay.
That's what I did, but it's a little tricky. It depends on which thing you use to view it.
Okay, let's try showing just one
Okay,
application.
so I think we are now live, and so Gabriele will be talking to us about this work, telling us that interacting seems unreasonable in time and space.
Okay. Can I start?
Please do.
Okay. So this is a joint work with Beniamino Accatori from Unreasonable in Paris and my supervisor in Bologna, Ugo Del Lago. I'm going to present some work that has already appeared in different venues, PPDP, Popul, and Leaks of this year. And so I will do some I will give you a bird's eye view of this research line that we have done. So I will not go into every detail, of course. This work puts together different research topics in the theory of the lambda calculus, which are mainly geometry interaction, initiative, the program initiated by Girard at the end of the 80s, and then the study of reasonable cost models, and the study of abstract machines. So I will briefly review all of these topics. So let's start from the part about the complexity of the lambda calculus, and so about reasonable cost models. We put ourselves in the simplest possible setting for the lambda calculus and for the programming languages meta theory, that in our opinion is the closed call by name lambda calculus. So we are, of course, Turing complete already, and we have no types, and we do not evaluate under abstractions. So terms are just variables, applications, and abstractions. Contexts are just weak head context, so the whole or a context applied to a term. And reduction is beta reduction that can be applied inside any evaluation context. This evaluation policy is deterministic. So the setting is very simple, and of course, since we are Turing complete, we have lambda terms that may diverge, for example, omega. Okay. Now let us consider the problem of computing the complexity of a lambda term. So evaluating a lambda term, how much does it cost from the complexity point of view? How much resources one needs to evaluate a lambda term from the time point of view and from the space point of view? So the point is that typically resources are considered on Turing machines. So in some way, we have to put in correspondence some cost measure on the lambda calculus with the typical complexity measures of Turing machines. And the typical proposal by Slot and Emde Boas is that reasonable machines have to simulate each other with a polynomially bounded overhead in time and a constant factor overhead in space. And in particular, Turing machines and random access machines are reasonable with the usual cost models built on that machines. So, of course, for Turing machines, the time cost model is just one transition of the Turing machine, and on the space cost model is the maximum size of the tape that is consumed during the computation. So the point is, can we implement the lambda calculus in a reasonable way? And this question is not trivial, of course, because the lambda calculus is a completely different model of computation. So let's start from the time constraint. So we need a polynomial overhead time simulation of the lambda calculus into Turing machines and vice versa. So let us try to consider the number of beta steps as the time cost model of the lambda calculus. Does this work? We have to consider the two different directions of the simulation. We begin with the direction in which we have to simulate Turing machines in the lambda calculus, and this direction is quite easy. We can encode Turing machines into the lambda calculus so that the overhead given by the simulation is polynomial and in particular linear. And this was, I think, well known in the folklore, but has proved in some unpublished notes by Ugo Dallago and Beniamino Accatoli, and these were used in their works. The other direction, the direction in which we have to simulate the lambda calculus into Turing machines, is actually more delicate. And this is because of a phenomenon which has been called size explosion. So what is this phenomenon? The point is that there exists a family of lambda terms indexed by n, such that the size of these terms is linear in n, and the number of steps that they require to reach the weak head normal form is also linear in n, but the size of this weak head normal form is exponential in n. So there is a mismatch. If we consider naively the number of beta steps as a time cost model, then we come up with the fact that the space consumed by the computation, because of course we have to write this normal form in some way in our Turing machine, is exponentially bigger than the number of steps that the term needs to reach the normal form. And this is impossible because, of course, space consumption cannot be bigger than time consumption on Turing machines. So we have to, in some way, do some clever trick to solve this problem, and one of the ways in which this problem can be solved is using abstract machines. For example, Crevine's abstract machine that we have already seen in the previous talk. There are also other methods, for example, considering a calculus of explicit substitutions in which we can share some radixes. So, however, the problem is somehow delicate, but can be solved quite easily. So we are okay for the time. There is no big problems. Now the point is that we need also a constant overhead space simulation, and in particular, it is not clear which is the space cost model for the lambda calculus. The most natural one would be considering the size of the term under evaluation, so the maximum size that the term under evaluation gets. However, this does not work naively, and in particular, because of size explosion. So we have that space can be exponentially bigger than time. So one could say, well, you have solved the problem for time using abstract machines or using a form of sharing. So let's use the same trick also for space. However, this does not work. And I'm sorry, in particular because abstract machines, as well as the calculi of explicit substitutions, use space which is equal to time. And so from the complexity point of view, this is problematic. They use this kind of space because they save every regex argument, and so they save all these arguments in some data structures. However, this is problematic from the complexity point of view, because if we have that space consumption is equal to time consumption, then complexity classes such as log space cannot be captured, because of course in log space we have that space is logarithmic in time. So using naively abstract machines does not work. So we have to consider some different mechanisms. So this was about abstract machines that are based on environments, typical abstract machines such as Krivins, or calculi of explicit substitutions that actually are very related to abstract machines. So in the literature, there is also another abstract machine that was pioneered by Danos and Renier and Yamaki, and which was claimed to be very parsimonious in space, because it uses space in a completely different manner, for example, from environment machines. So we have thought that maybe this kind of machine that is based on Girard geometry interaction could be the solution to obtain some reasonable cost model for space. In particular, the ideas of these abstract machines is that we do not trace all the encountered beta redexes, and so this way space is disentangled from time, which is our main goal. There is a quite complex backtracking mechanism to retrieve beta redexes, and so we actually waste some time to gain space. Computation is local, so if we consider the abstract syntax tree of our lambda term under evaluation, computation is like carried out by a token that travels inside the abstract syntax tree in a local way. So there are no jumps, let's say. Instead, in Krivin machine, for example, when we reach a variable, then we jump to its argument, while in the interaction abstract machine, computation is always local. And so we can see the computation as a token that travels inside the term. And finally, the code never changes. So we have a static part of the machine, which is the code, the code that we are navigating. In the interaction abstract machine has already been used different times to prove some results about space complexity. For example, Maki devised a very small runtime system for PCF and claimed that the evaluation was space efficient, actually without any proof. Dangika used the ideas from geometry interaction and game semantics to devise a compilation scheme for higher order functions to digital circuits, which of course have finite memory, so their space is highly constrained since it's constant. Dalago and Schoep devised a functional programming language that is constrained to work in log space, in the spirit of implicit computational complexity, and used ideas from the geometry interaction to devise such a language. And finally, Aubert and co-authors used ideas from the geometry interaction to devise a restriction of prolog that is constrained to work in log space. So this machinery, the machinery of the interaction abstract machine, has already been fruitfully used to obtain some results about space complexity. So let us see quite briefly how this abstract machine works. We need the concept of a position. A position inside a term is just a pair formed by a subterm and a context, so that we can identify the position of our token. For example, here the position is inside there is lambda, and is indicated by this position, which is t, and the context, which of course is lambda x dot the whole. And now, how does the machine actually work? We do not save beta radixes. So when we reach our radix, for example, here we have lambda x dot t applied to u. We start from the root of the radix, let's say, with the token, and then we go inside the left-hand side, and the token changes color. So from black to white, we go inside the left-hand side of the application. And then, since the token now is white, then we can enter inside the lambda abstraction, and the token returns to be black. So the token is untouched when it traverses a beta radix. So this is one mechanism. We evaluate, let's say, modulo beta radixes. Then, of course, we have to find the head variable of a term that later will be substituted, let's say, by its argument. So the abstract machine looks for head variables, and in particular looks for head variables when it is in, we say, in read mode. So, for example, if we are if the token is in read mode, so is querying for the head variable, and then through this mechanism of traversing the term modulo beta radixes reaches a head variable, then it jumps to the binder of this variable, and we consider this computation as local, not as a jump, because we use a proofnet-like notation. So, of course, variables are connected to their binders, and so we go to the binder of the variable, of the head variable, and the mode changes from red to blue. And so now the machine is looking for the argument of this variable. Okay, so of course, when the argument is found, the argument has to be evaluated. And so, for example, let's say we are in this position, so we are in front of the binder in the left-hand side of an application. Of course, the argument of the variable that was inside t is u, and so we are in blue mode. We are looking for the argument, and then we go again into red mode in front of the argument. So because we have to evaluate the argument u, and so the process begins again. Of course, I have hidden some details. The actual abstract machine is much more complicated. There is a backtracking mechanism, which is quite complicated, and the actual data structures used by the machine are much more complicated. So we do not use only black and white and red and blue, but we have a quite complicated use of data structures, let's say quite reminiscent of those of the Krivine abstract machine, because we have also here some mutually recursive definitions of data structures. So we do not have environment and stacks, but we have those two data structures that we call history, that we call log and tape, that are formed by some complex data structures. But of course, understanding the full mechanism of this machine is quite complicated. The important point of view is that we have an implementation theorem, a correctness theorem, that says that a lambda term T has a weak head normal form if and only if the interaction abstract machine terminates on the term T. So this machine is sound and adequate for call by name. Okay, so this was the first part about, let's say, the complexity and the interaction abstract machine. So now let's see how we can capture the complexity of the interaction abstract machine by the way of intersection types. So we have already seen in the talk of Daniel that he captures, he puts in correspondence the lambda mu calculus and the Krivine machine, and he has pioneered the complexity analysis of the Krivine machine and the lambda calculus with intersection types. So we try to do the same in the context of the interaction abstract machine. So we consider non-idempotent intersection types that we call sequence types, and they are very simple. We have a unit type star and arrows. Arrows are sequences, arrows are linear type, and sequences are just sequences of lists of linear types. So we have two levels, the linear level and the sequence level, that is the exponential level in linear logic terms. And we consider non-commutative sequences, but this is just for technical reasons. Okay. So this is the grammar, the typical grammar of non-idempotent intersection types. And of course, it has already been proved by Daniel and also by others that a term T is typable, in our case with star, because we are weak head. We are considering weak head normalization. So a term T is typable with star if and only if the term T has weak head normal form. So this is well known. So just for those who are not very into the non-idempotent intersection types word, I will say a few words about them. And in particular, these kind of intersection types are just another way of formulating the typical operational and denotational semantics of the lambda calculus based on linear logic. So from the operational semantics point of view, we have a linear substitution calculus by Beniamino Catoli and Delia Kessner, which is actually isomorphic to proof-net reduction. And we have Krivine's abstract machine. We have the interaction abstract machine, and also Damiano Mazza polyadic approximations, or also dubbed as rigid resource terms by other people. So all these different topics are actually very similar, and they are the linear logic decomposition of the beta rule seen in different ways, all operational. While from the denotational point of view, we have the relational model of linear logic, of course, and also game semantics. So for example, the interaction abstract machine is very related to the Abramsky and Courtois game semantics, while the non-idempotent intersection types are actually a syntactic way of seeing the relational model. So all these aspects are very linked. Of course, we are doing an operational work, so we consider intersection types and the interaction abstract machine. However, the connection between these two topics were not present in the literature. So let's say, let's see the typing rules. These are very standard and are the standard system of Daniel de Carvalho for call by name. And so I will not spend too much time. Of course, since we are weak head, we can type abstractions with the type star, and the other typing rules are standard in the non-idempotent setting. So the lambda is typed with the arrow, of course, the axiom for variables, and applications need, of course, that the argument is typed as the left-hand side of the arrow. Okay, so this is very standard. Our intuition, our contribution is that we were able to see the interaction abstract machine structure on type derivations. So if we consider a type derivation for a term t ending in star, so a typable term t, we can consider a token machine built on the type derivation, on this type derivation, and this token machine starts from the root occurrence of star, and then we can consider a machine that allows the token to travel from one occurrence of star to the following in a very natural way. And in particular, this machine turns out to be strongly bisimilar to the interaction abstract machine. So actually, we can define the interaction abstract machine inside type intersection type derivations. What is the interesting thing is that we do not need any data structure anymore. So the multiplicative part is handled by types, while the exponential part is no more needed, because in non-idempotent intersection type derivations, all the arguments of a regex have already been copied the right number of times. So every use has a different subtype derivation. And so every part of the type derivation is used only once in a linear way, of course. This is the main connection with the linear logic understanding of the lambda calculus. And so actually the interaction abstract machine built on type derivation is very, very easy. Here I can show you an example. We will not see the full evaluation of this lambda term, but just to show you how this is very simple. So we have typed this lambda term, and of course the abstract machine defined of the type derivation starts from the root occurrence of star, which I have dubbed with 1 because it is the first state, and then the token travels in the natural way following all these occurrences of star. So this is the first one, and then it goes into the left-hand side. This is the second one, and then the third one, again in the left-hand side, because we are traversing beta redexes, right? There are two beta redexes, one and the other one. And so we are going modulo beta redexes, and then again we are entering inside the first abstraction, and then instead the second abstraction, because we have to pass through two radixes, and then we go to the head variable, and of course from the head variable we jump to the binder of that variable. And so actually we see that every occurrence of the type star is a state of the interaction abstract machine. This observation is crucial. So actually computing the runtime based on type derivations, the runtime of a lambda term t based on its type derivation is very easy, because there is only one initial state. We can prove that there are no cycles, and thus as a consequence all states are reached exactly once, and thus the runtime is exactly the number of states, and this is exactly the number of stars in the derivation. And so it is very easy to compute the runtime based on the type derivation, because we just have to count the number of stars. And this is very easy by using a weight system on judgments. Okay. From this observation, we see that the runtime of the interaction abstract machine depends on types, because of course the number of stars in a derivation depends on types. While in the case of the Krivine abstract machine, the number of steps depends just on the size of the derivation. So types were hidden in this count. And we know that the Krivine abstract machine is reasonable for time. Instead, we can see that there are types, there are terms that have types which are exponential in the size of the term and in the number of beta steps. For example, if we consider the identity applied to itself n times. So the interaction abstract machine can be very inefficient in time. While of course the size of the type derivation for term t is always polynomial in the size of t and in the number of beta steps. This does not say that the interaction abstract machine is unreasonable, because we should consider only the terms which are the image of the encoding of Turing machines. So we will see these in a moment. But we have already a result that says that in general the interaction abstract machine is inefficient when terms use higher order types. So from now we know that we can characterize the runtime of the interaction abstract machine by intersection type derivations. So another problem is, can we capture also space? Well, in order to capture space, we need to refine the time system. I do not have so much time, so I will not go into the details, which are quite technical. The point is that we do not have any more sequence types, so linear list of linear types, but these linear types are organized in some tree-like fashion. And in particular, we can get a space type measure on these three types. The inference rules are quite standard, are very similar to the rules that we used before, the original of Daniel de Carvalho system, but they are adapted to take into account these tree type fashion. And in particular, you see that here we put into a multiset into also the types in the type environment. However, this is a technical, convenient way to capture space. And actually, we do not have a clear intuition of why this works. Then we can, as for the time, we can weight these typing rules, and we have proved that again, if we type a term t with star and a weight w, then this term t takes exactly space w when evaluated with the interaction abstract machine. So we have characterized also space consumption by the way of intersection types, and this is actually the first time that space is captured using intersection types, and in particular because the interaction abstract machine has a non-trivial space behavior. So the space usage is not incremental, but sometimes it grows and sometimes shrinks. Now the problem is that we would like to see if the interaction of the machine is invariant with respect to time and/or space, and in particular, we have to implement the Turing machines in the lambda calculus, and then execute these lambda terms with the interaction abstract machine. And the point is that the fundamental ingredient of this encoding is the fixed point combinator. And in particular, we devised the types for the fixed point combinator, and we find out that just using these types, it is possible to say that the interaction abstract machine is not reasonable in time. And in particular, because of this type, this is a Fibonacci-like recurrence if we count the number of stars inside here. And so this number is exponential in n, where n is the runtime of the Turing machine that we are considering. So we have that the runtime of the interaction abstract machine is exponentially bigger than the runtime of the Turing machine that we are implementing. So we do not have a reasonable implementation. Okay, and finally, we can also consider the space counterpart, and so devise types, 3 types also for space. And also here we can very easily notice that the space consumption is actually linear in the Turing machine runtime. So we have a time that space again is linear in time, and so we are not able to capture, for example, log space. So we do not have a constant space simulation, but we have a simulation which is linear in time and not in space. So actually, we find out that we are not reasonable also in space. And this is it. I think there is time for a quick question. Thank you.
Very good. Thank you very much, Gabriele. Are there any? I see Joe Wells is asking about maybe your slides, if you could make those available.
Yes.
It sounds like he's interested in looking at them in more detail.
Yes, of course. However, also the papers are already published, so one can see them also. But however, I will make the slides available.
Great. All right. Well, I'm off to the next talk, and everyone else, you can stay in this room for the next talk, or you can move to the discussion room to talk more about this paper. So again, thank you very much to Gabriele.
Thank you.